In this video, we're going to talk about the fundamental theorem of line integrals. I love this theorem, and one of the things I really love about it is that it is a very natural extension of the original fundamental theorem of calculus that you would have seen back in first year calculus. Now, in our previous video on conservative vector fields, we saw this example. This field was a model for gravity because it was just pointing straight down. And we had some path, but in fact we could take many paths. And we saw in that video that the line integral, the one that represented work, it only depended on the endpoints for this particular field. That is, this field was conservative, which by definition meant that this line integral was independent of the particular path, it just depended on the endpoints. So in this video where we're talking about the fundamental theorem of line integrals, we're going to be talking exclusively about conservative fields. When you have a conservative field, you can get this fundamental theorem of line integrals. Okay, well, we can't go to the fundamental theorem of line integrals without reviewing the fundamental theorem of calculus. So let me just quickly put it up on screen. I'm going to say it in maybe slightly a different way than you've seen previously. I'm going to say if you have a derivative in f prime, and that's continuous on some interval, then the integral of this derivative is just the difference between the endpoints. Okay, so now let's go and upgrade to the fundamental theorem of line integrals. So it says a whole bunch of different things. Perhaps the first thing to focus in on is the assumption that our field f can be written as the gradient of some potential function, little f. And at the end of the previous video, I had spoiled to you that conservative fields were going to be equivalent to this particular property. So nevertheless, I have my field being not any field, but the specific case where it can be written as the gradient of f. And then the result that I get is that the line integral is much like in the fundamental theorem of calculus. It's just the difference of the function f of b minus f of a. I have a few other things stated here in my theorem. First of all, I talk about my curve, which is a nice curve. It's smooth, I mean its first derivative is continuous. And I have some parameterization r of t, and so t was my time interval, and little a and little b are the endpoints of my time interval, and then big A and big B are the points in space that happen at the corresponding time. So the position at the time, little a, is going to give you the point, big A, and so forth. So this theorem is really very similar to the fundamental theorem of calculus. Since my assumption on the field capital F is that it's the gradient of little f, and gradient is sort of a generalization of the derivative, I'm doing a similar idea. I'm saying I want to integrate a derivative, and then that will just be a difference of the endpoints. So this then really be thought of as that extension of the fundamental theorem of calculus. Now, I actually want to prove this theorem. I love this proof because it cut directly to the core idea. So, okay, let's try to integrate this. I have an integral of f dot dr. And the first thing I'm going to do is put it into its parametric form, that is an integral with respect to t. So we write it as the f dot r prime version that we've seen previously. Now, we have the assumption that capital F can be written as the gradient of lower f. And so let's just actually put that in here. I've just replaced the capital F with the gradient of lower f. Now, this we've actually seen way back in multivariable calculus. I can rearrange this by the chain rule. So let me state the answer and then we'll investigate it. I claim this integrand is nothing but the derivative of the composition f of r of t. Well, why is that the case? Let's think about f of r of t. This composition results in a function from just r to r. T is a scalar input. It goes in, and yes, r has multiple different values, but then f was a scalar function. It took the rn, say, and spat out an r again. So this, as a composition, just goes from r to r. And then if I want to take the derivative of that composition, I have to use chain rule. And so you take the derivative of the outside function effectively and dot it with, well, the derivative of the inside function. That's what gives this middle line. Okay, so now that we've done that chain rule trick from multivariable calculus, now we can go to single variable calculus because I have a single variable integral and it goes back to dt. I have a single variable derivative ddt. I can just do single variable calculus stuff here. In particular, the integral of a derivative by the fundamental theorem of calculus is just plug in the endpoints. So it's the function f of r of t evaluated at b, and then subtracting off that evaluated at a. That is the fundamental theorem of calculus. And then I'll just rewrite, instead of r of little b, I'm just going to write big B, and instead of r of little a, I'm just going to write big A. And that's our proof. And I think what's core here is that this proof is just some basic manipulation, like the chain rule. But then it's just saying we have manipulated it so that we can apply the fundamental theorem of calculus, the original fundamental theorem, and then that is immediately given this generalization to the fundamental theorem of line integrals. So when I say it's a generalization, I don't just mean that the formulas look similar, I mean that it was integral in the proof that we use the fundamental theorem of calculus. So looking at the theorem one more time in its full glory, we have that the integral along curve of f dot dr is just equal to f of b minus f of a when the field can be written as the gradient of some potential function, the gradient of some little f. Now I'm going to go back to this claim that I actually spoiled in the previous video on conservative vector fields. If you recall, a conservative vector field was one where the line integral was independent of the path. And the claim is that a continuous field is conservative if and only if, so both directions, this field can be written as the gradient of a potential function. Now, what we've just seen is the proof of, namely, because of the fundamental theorem of line integrals, if you have it written as a gradient, then the result that you got was just the difference of the ended points, clearly did not depend on path, and thus meant it was a conservative field. I still technically owe you the other side of the proof that says if it's conservative, then you can write it as the gradient of a potential function, and thus the fundamental theorem of line integrals is going to apply. But I'm actually going to skip the proof only because of pedagogical reasons here, and you can find it in the Thomas Calculus textbook that we're using for this particular course if you want to check it out.